Let's make it full screen. All right. So welcome to the second week of our Reservoir Petrophysics class. The topic of this week is Reservoir Petrophysics, Capillary Forces and Wettability. By the way, did anybody started recording? No?
Yes.
Start.
Okay, good. All right. So, capillary forces and wettability we will continue with in the second week. This is a crucial topic actually, because if you are on the way of learning petrophysics, so you have to pass from this way, and you have to have an idea regarding on capillary forces and wettability definitely. Okay. So because of that, I had to put this topic in the second week. When I checked the previous syllabus, I did not see this topic, but this is very crucial, so it has to be in there. So I wanted to start actually with this one. We will continue. Okay, what about the capillary forces? Any idea? You can tell anything about capillary forces? What do you know from second class, from previous years? Anything? Who can tell? Please, if you want to talk, first tell your name, and then after telling your name, you can give your comment, answer, whatever. Okay. So, what do you know about capillary forces? Capillary, what does it mean? Capillary forces. Any idea? Nope. Okay, I will continue. Capillary forces included actually it happens in micro scale. Okay, in the porous media, inside the pores. Okay, the physical effects are not like the ones that are happening in real world. Okay, in the macro world, that's in our world. So here the forces are a little bit different. So the physics rules which describe these phenomena, these forces which are happening in porous media inside the pores, is totally different. Okay, so today we will have a path to learn this one, to learn a little bit about this one actually. So we will start with the interfaces, what surface energy means in microscale, the capillary pressure in porous media, measurement of capillary pressure, and hysteresis areas we will talk about in AMOT and USBM methods. J function, a little bit pore size distribution, and permeability from capillary pressure will be included. Most of them will be included, and you will definitely have an idea regarding on the capillary forces and the wettability phenomena which is occurring inside the pores, in porous medium. Okay. So regarding on the capillary forces, interfaces, we can talk about 6 different interfaces actually. 3 of them belong to fluid-fluid interfaces, and the other 3 rock-fluid interfaces. Okay. For the fluid-fluid interfaces, we can talk about the interaction between water phase and oil phase, water phase and gas phase and oil phase. Okay. So in reservoir, in porous rock, what we have 3 different phases, right? Oil, water, and gas. So each of them has an interaction with another one. Okay. According to the certain pressure and temperature, some of them can be miscible, some of them can be soluble inside the other one. For example, if you arrange the pressure and temperature, what will happen? Some part of the gas phase can pass to oil phase, or a soluble gas which is already inside the oil phase can pass to gas phase. The same thing is possible for water and vapor as well, right? So the interactions between these 3 phases are very important with each other, first of all. And the second one, their interaction with the rock. Okay, they are also in contact with the rock surface, right? Oil, water, and gas in contact with the rock surface. So they have another interaction with the rock. Okay, actually, rock, the type of rock and the tendency of rock to choose a fluid, to like a fluid, actually, is very crucial because it totally affects your recovery factor. Because we mentioned this before, if your rock likes water, this is a very good advantage. It's a water wet, we call it. And if your rock likes water, what happens? It has a tendency to get rid of the oil phase. So when you are producing from your well, this will be a very good advantage because the remaining oil, residual oil, will be lower compared with the oil wet rock. Okay, so this is very crucial. So we said water oil, water gas, gas oil interfaces for fluid interactions, rock water, rock oil, and rock gas phase interfaces for rock fluid interaction. These are the interfaces we are dealing with. Okay, let's pass to capillary forces, surface energy. Surface energy, actually, this is the energy required to create an interface from bulk fluids. It also defined as the force required to extend a surface in force per unit length. Okay. In CGS system of units, what is CGS system? Any idea? What's CGS? CGS. Did you heard this before?
No, teacher, I don't hear.
Okay, it's very crucial. I think you know this from high school even. CGS, centimeter gram second. Okay, centimeter gram second system. All right. Centimeter gram second system. In CGS system of units, surface energy or tension is given in erg per centimeter square or dienes per centimeter square. Numerical values are identical. So a reasonable value for water oil surface area per cc of rock is 1 square meter. For a surface tension of 30 ergs per centimeter square, the surface energy at the oil-water interface in 1 centimeter square, 1 cc of rock is 300,000 ergs. Okay, 300,000 ergs. Okay, so in this case, what can be the energy stored at the oil-water interface in 1 acre-foot of reservoir? Okay, when we say 1 BTU equals to 1 E, 1 force up to 10 ergs. Okay, do you have an idea what it can be? Or how we can solve this? No? Okay. So this can be one of the quiz questions. All right? So try to find this, how we can solve it. It will be around 37,000 BTU, something like that. Okay, so that's this. Capillary forces, capillary pressure. Capillary pressure, we call it PC, okay, PC, is the pressure difference across an interface separating two miscible fluids confined within a capillary. The pressure in the fluid on the concave side of the interface is always greater than in the fluid on the convex side of the interface. Actually, the water wets the walls of the capillary, but the oil is non-wetting and is resting on a thin film of the wetting fluid. Okay, so the pressure within the non-wetting fluid is greater than the pressure in wetting fluid, and consequently, the interface between the fluids is curved convex with respect to the non-wetting fluid. Okay, the capillary pressure actually is defined as the pressure difference between the non-wetting and wetting phase. So for example, in here, for example, let's see the plot one, figure one, sorry. In the figure one, which one is the non-wetting phase? Any idea? Which one can, according to this description, which one can be the non-wetting phase?
I think P1. P1 is
Second one.
Who is speaking? Tell your name and answer question.
Akışın araçlı, I think P1 is non-wetting phase
P1 is the non-wetting phase
in the first picture.
in the first picture. Okay, first of all, guys, let me repeat this one. Do not talk before telling your name. First tell your name, please, because I want to know each other, okay? So please tell your name first and give your answer, okay? I cannot see you
Okay.
now, okay? So tell your name and give your answer. Which one is the non-wetting phase for the first one?
That's Diana, teacher, and I think the second one is wettable because here the angle smaller than the 90.
Okay, so P2 you say non-wetting or P1 non-wetting?
P1 wetting and P2 non-wetting, I think.
Okay. Any other idea?
My name is Rashad Musayev, and I think in first picture, P2 is wetting phase,
Mhm.
P1 is non-wetting, and in second picture, P2 is non-wetting phase.
P2 is non-wetting. Okay. So you say P1 is non-wetting for the first, P2 is non-wetting for the second.
Yes.
Right? Okay,
Right.
so actually this is the correct one. P1 is non-wetting phase in the first one. Okay? P1 is the non-wetting phase and P2 is the wetting phase. How I understand this one? Because you in this one, if you want to understand which one is non-wetting, which one is wetting phase, you have to check their interaction with the surface. So see the surface in here, okay? What's happening? The P2 in the second phase has a tendency to spread on a surface, okay? It wants to spread on a surface. You see in this part, but P1 doesn't have this type of behavior. Its pressure is much more in the center. Its pressure is forcing, yes, but when its pressure is forcing, it doesn't have a tendency. The P2 doesn't have a tendency to be flat or something like that. As you can see, it has a tendency to catch the surface. Okay, to catch the surface. Still, it's continue to catch the surface. Doesn't leave it, right? So because of that, you can understand that P2 in here is the wetting phase compared with the surface interaction. Okay. So in this one, P1 is the P2 is the non-wetting phase and P1 is the wetting phase because of the same behavior. P2 pressure is higher, so we can say that if the pressure is higher, that phase mostly becomes the wetting phase. Okay, becomes the wetting phase. Sorry, non-wetting phase. Non-wetting phase. Okay, so in this figure, P2 is the non-wetting phase in this case. Okay. Capillary pressure is the difference between non-wetting phase and the wetting phase. Okay, it's described as this one. So let's make some derivation regarding on the capillary pressure equation. It will make the things more clear, I think. Okay. This is a figure which has been taken from the TIAPS book. All right, it shows the radius of curvature of the interface between the two fluids. The work is done on the interface to expand the surface against the interfacial tension. Interfacial tension if we are talking about the facial tension, it means that the tension between a certain liquid and air. Okay. If we are talking about the interfacial tension, it is the interaction between two liquids. Okay, two liquids. This is crucial. Okay, so what is going on? Think about that. This surface ABCD is the surface that we see somewhere in here. Okay, somewhere in here. In micro scale we are talking about. Okay, somewhere here I am. So what's happening? The P2 is trying to push from here. Okay, or somewhere here I am, because let's talk about this one because P2 is bigger. So I am somewhere here, and P2 is pushing this, okay, and expanding the fluid, okay, and by time the fluid will expand from here, for example, to here, from here to here, right? So because of that, let's make the mathematical derivation of this one. In the first one, this is the first surface, and ABCD in the second part, the ABCD powered this one. Okay, it's expanded by time. Okay, so on the surface, however, the molecules are attached inward and on all sides, but there is no outward attraction to balance the inward tug on the surface molecules. Okay, so this imbalance of forces causes the surface to contact to the smallest possible area and produce a surface tension. Okay, and this surface tension expressed as Newton per meter. Okay, and divided by m, Newton per meter. So work must be done to extend the surface in opposition to the surface tension by forcing molecules from the interior to the surface. Okay. So this indicates that there is a free energy associated with the surface that has the same dimensions as the surface tension. Okay. So let's consider a segment of the interfacial surface separating two fluids with a pressure difference across the interface, producing a curvilinear rectangle as illustrated in this figure. Okay. So both sides. Again?
What's L here? L1 and L2.
Okay, so L1 and L2, I am coming to that. No worries. Let's continue. Okay, L1 and L2. Mostly we say A to B as L1. This is a curve actually, right? This is not a certain rectangle. This is a curve. So A from A point to B point, let's say L1 in here. B to C, let's say L2. Okay, let's say L2. So area of ABCD will be very close according to this one. I am talking about macro scale. So because of that, I can make an assumption that area ABCD will be very close to L1 times L2. Okay, L1 times L2. Okay, so area A powered, B powered, C powered, D powered. Okay, the expanded part. Okay, what it will be? L1 plus L1 divided by R1, which is R1, okay, times dz, the our increment, okay, sorry, the increment, okay, and multiply by the same for L2, and this part we said this is a curvature, right? We said this is a curvature. So there will be a center of this curve, L1 curve. There will be a center of L1 curve. We call it O powered. Okay. There will be a center of BC L2 curve. It will be somewhere like this. Okay, and with the diameter, semi diameter of R2. All right. So think about that. This is a curve. So if it is a curve, there will be a full circle of this that can be, right? It's a curve. So when I compare this full circle, the center of circle, this will be. And for this one, for AB L1, it will be here, somewhere here. Okay. Okay, I think this is clear.
Okay.
So L1 plus L1 divided by R1 times dz. L2 plus L2 divided by R2 dz. When we multiply these two, so I will reach the area of my new interface. Okay, this one. Sorry, the new interface area I will reach. Okay, so let's some arrangement on the equation. L1 times L 1 plus dz divided by R1, dz divided by R2, plus dz square divided by R1 and R2. Okay, so this will be a very small actually amount, so it can be neglected, and I can reach to this formula. Let's see. Yes, so the new formula between I want to describe the amount of this expansion actually, right? So because of that, I will take the differences of the areas. A powered, B powered, C powered, D powered minus ABCD. So this is given as the equation 5.4 L1 L2 times dz times 1 over R1 plus 1 over R2. Okay. So if we talk about the works, actually, if we talk about the works, we can say that the isothermal work, actually it is Newton per meter times meter square will be, okay. So the isothermal work required to expand the area against the surface tension is given in 5.5. Okay, this is sigma. This is the interfacial tension, called interfacial tension between two liquids. Okay, so the work one can be described like this. The second one, the isothermal work done by the increase of pressure to advance the surface a distance dz, in a distance dz, called work 2. Okay, and it described like this. So the first work has been done by the interfacial tension, the tensions, okay, and the second one has been done by the difference of the pressure, okay, as can be seen in here. So these two works is described in these two formulas. So by using these two formulas, okay, we can actually, when we make an equation, we combine these two equations. What happens when we cancel the common terms yields the capillary pressure as a function of interfacial tension, actually, and the ratio of curvature. So I said there will be neglected place in there, dz square. See this one, okay. When we make our neglections, so we got the capillary pressure value as the function of the interfacial tension and the radius, different radiuses of my curves L1, L2, okay, as a function of these. So, however, when a porous medium actually is considered, R2 may be negative as well. Okay, so let's make the equation more general, and I can write the equation as plus minus here. So when you come to the real situation, there can be a minus also actually how can I tell this one? The medium can be in the minus when we compare it with R1. When we compare it with the R1, if you put in a cylindrical order, the R1, the R2 can be in negative part. So because of that, you have to give the negative sign to that. Okay. So it can be plus minus as well in 5.8, as you can see. So in the end, if the radii of the curvature are equal, you mean R1 equals to R2. So what happens? My formula changed as 2 sigma divided by R, 2 times of interfacial tension value divided by the radius. Okay. All right. This can be given. Okay. So let's continue. Let's continue at this point. So in figure 5.3, okay, it's a kind of exaggerated view of a capillary tube which contains water as the wetting phase and in contact with a non-wetting fluid. Okay, so this is much more detailed explanation actually. It can be gas or oil, but in the figure it's shown as oil. So the radius of the spherical interface is larger than the radius of capillary. Okay, radius of capillary, and the two radius are related by the cosinus of the contact angle. So I call it theta. Okay, so as you can see here, this is my theta, and when it is theta, this will be theta too. Okay, so cosinus of the contact angle. Okay, the contact angle means I have two immiscible fluids here, water and oil. They both are in contact with a solid surface. Okay, so the angle of these two making with the surface is my contact angle. And when this is theta, this will be theta 2. Okay, according to the geometry, this will be theta 2. All right. So herein, the cos theta is RC divided by RSI. RC is actually the radius of the capillary tube. Radius of the capillary tube. Here it's showed as RL, but it's RC. Okay, the radius of the capillary tube. And RSI is the radius of the spherical interface. Okay, we called it RS in here. RSI, the spherical interface radius. Okay. So, substituting RSI for R in capillary pressure equations in terms of interfacial tension. When you see IFT, it means interfacial tension. Okay, in some papers, in some books, it called as IFT, interfacial tension, contact angle, and radius of the capillary tube. Okay, so my equation becomes what? 2 times my interfacial tension times the cosine of the theta angle divided by RC. This is the generic capillary pressure description, capillary pressure formula. Okay, so I am putting here the effect of my because I would like to put the effect of my contact angle, because it's a kind of description of the wettability of two interfaces. Okay, so because of that, putting cos theta is crucial in here. So the generic equation of capillary pressure is 5.11, equation 5.11. Okay, this is we called here 5 because this is the fifth section of the TIAPS book. Okay, I thought that it will be easier for you to follow from the book, so because of that I put same values, same equation values. Okay, all right. So capillary rise. Okay, this is figure 5.5. The immensity of capillaries having different wettabilities, 3 different scenarios put in here. So when a capillary tube is inserted below the interface of two-phase system which are immiscible, which are not miscible with each other, the meniscus of the immiscible fluids in the capillary will be either, first, it can be concave with respect to the denser phase. In the first one, you can see that, okay, with respect to the denser phase, which will rise above the interface between the two liquids outside the capillary. Okay. Second, straight across the capillary and the level with the bulk fluids interface. Or the third one, convex with respect to the denser phase and below the bulk fluids interface, as illustrated in this figure. Okay. So actually the shape and the height of the meniscus depends on the relative magnitudes of the molecular cohesive forces and the molecular adhesive forces between the liquids and the walls of the capillary. Okay, capillary tube. So according to these differences, it can be shaped as, for example, according to the capillary pressure differences, it can be shaped, the liquid level column can be shaped like this, or can be same level, okay, can be in same level with the total oil-water interaction level, or it can be lower than that, okay, according to the difference. So let me ask another question. For example, here we see the thetas, right? We see the thetas in here. In the first one, the theta is this. The theta is in the first one. The theta is this one. Okay. In the third one, the theta is this one. So which one is oil wet? Which one is water wet?
The third one, sorry, sir. I am Abdul Hussein. The third one is the oil.
The third one is oil wet. The
Yes.
first one is water wet, you say, eh?
Yes.
Why?
Just a minute, sir. Sir, it's the opposite. I mean,
Okay.
the third one is the water wet, and the first one is oil.
Teacher, can I answer?
Please, your name.
Akshin.
Okay,
So,
Akshin.
as Abdul Hussein said, first one is water wet and third one is oil wet. Because if the contact angle between two immiscible fluids are less than 90 degree, it's water wet, and if it's greater than 90 degree, it's oil wet.
Okay, what about the second one? What about the second one?
It's full weight. Both fluids has same wettability.
So what can be the contact angle?
It will be 90
90
degree.
Exact 90
Nice.
degree.
Correct. Correct. 90 degrees. So the first one is water wet, definitely. Actually, when I see in here, according to the figure, it's strongly water wet, actually. Okay. So the third figure is oil wet, definitely. It's between the oil wet to strongly oil wet somewhere, maybe 140 degrees, 50 degrees. So the second one is same angle it is. So we can say that this is neutral wet. Neutral wet. Okay. So if it is in 90 degree, around 90 degree, actually it is between, according to the literature, it is between 62 degrees and 133 degrees. We say it is a intermediate wet section. Okay, intermediate wet, and it is 90 degree. We call it neutral wet. Okay. So okay, very good, very good. Let's continue. Okay, so the denser fluid will rise in the capillary unit. The weight of the column of the fluid balances the pressure difference across the meniscus. Consider the surface of the meniscus in a circular tube of radius r as a segment of the sphere with radius r. Then cos theta, what happens? RC divided by what? RS. Okay. And substitution into equation 5-9. This was 2 times of my interfacial tension divided by R, right? When I combine these two, I achieve, as I mentioned previously, I achieved the 5.11. Okay. So downward force, we call it, we mention as W. Okay. Expressed in Dien's. One din is its value is given in here in terms of centimeter gram and second, due to gravity exerted by the cylindrical column. Okay, so the force down in the down direction, the force will be W minus B. What is B? What can be the B in here?
Archimedes.
Again?
Buoyancy teacher.
Buoyancy. Okay, very good. Buoyancy. So the force down will be the downward force minus the buoyancy force, right? So because of that, what I will do in the end, after shaping the formula, in the end, I will take the differences of the densities, water densities minus oil densities. So gravitational acceleration in here, okay, the column height, P, and RC. Okay, it's the function of these parameters. So this is the force down. Okay, so what about the force up? So the upper pressure, the force actually applied in the upper through to upper part, okay, will be again the function of the interfacial tension, my contact angle, RC of course, and P times RC square. RCs will go, one of the RCs will go in here, but it's not a big problem. So when I equate these two forces, because it's in balance, right? So I will say that force down equals to force up. So when I equate these two, I will get another capillary pressure equation. Actually, I will yield the same value, but in this time by equating the forces. Okay, I reach the same value by using the forces. Okay, so PC is expressed in Dean per centimeter square, as I said, and it is equals to millinewton per meter square, and also Pascal. Okay. So let's talk about the J function. What is J function? Actually, this is a dimensional analysis which has been done, okay, by substitution of the capillary pressure equation into cosonic Harman equation. Last week we talked a little bit regarding on there was a pet. There were two pets actually. Diana actually I think asked regarding on this. It will choose the harder way or easier way. You remember maybe the pets. So according to the wettability, definitely your fluid can choose the hardest way, longest way when it is reaching from one point to another. Or according to the wettability again, it can be choose the easiest way. So it's directly, because you are in the microscale, so it's directly related to the effect, the interaction between your two fluids and three fluids, whatever, and your rock surface. This is very crucial. So capillary pressure is one of the descriptions that describes this one. Okay, this describes the amount of this one. And G function is the another one actually. So I will directly give the G function formula in here. So capillary pressure can also be written as interfacial tension cos theta divided by your permeability and porosity ratio, and the square root of these actually. Okay. So J function formula will be capillary pressure times, okay, you have your capillary pressure values. It has been given to you. The capillary pressure is this one. It's described previously, so you can go from the G functions directly. So capillary pressure times your permeability divided by your porosity, okay, and the square root of these, and divided by your interfacial tension and cos theta. Okay, this is the formulation. So, for example, if you make a correlation regarding a certain situation, your G function and water saturation will in a shape like this, exponential decrease. It will show, okay, the line as the curve. It will show an exponential decrease. It's typical actually. It can be different in some parts, some points, but typically it shows an exponential decrease. So when I ask you the typical behavior of a J function with water saturation, you will say it's an exponential decrease, and you will draw this kind of figure. Okay. All right. So let's continue. Let's make a very basic example. For example, so it says that the fluid in a straight tube have an interfacial tension equals to 30 millimeters per meter, and exhibit a contact angle of 70 degrees and capillary pressure of 7.5 kilopascal. So what will be the radius of the tube? Okay, so herein I put my formula directly. Very easy, right? It's for example, my interfacial tension, it says 30. Okay, we put it. It's millinewton. I change it to Newton. Okay, Newton per meter it becomes. So your contact angle cos theta, cos 70, it's around 0.342. Okay, and your contact angle, it says 7.5, and I change it to Newton per meter square again. Okay, and I made my calculation, easy calculation, and I reached 2.74 times 10 times minus 6 meter. So it's nearly 2.74 micrometer. Okay.
Sorry, sir, I'm Mustafa Khaldun.
Yes.
Just I have a question. Every
Please.
time when we have K Pascal, when we want to change it to Newton meter square, just multiply by 3 power 9 power 3.
Yes, if you want, I can give you I have a actually PDF file regarding on this, the conversions. Okay, I will give you the conversions as well. Okay, so it will be easier for you. But it will be like this. So milliliter per meter, you have to change it to Newton per meter, Newton per meter square. Okay, because I want to make all of them same. How I can divide by kilopascal. Milliliter per meter to kilopascal. Okay, so I have to make my corrections. Okay,
Okay.
So I have to show it as in terms of Newton and meter for when we are talking regarding on the capillary pressure and the radius, tube radius, okay, capillary tube radius. So I will give a conversion table for you. No worries, I have some. I will share in the Teams. Okay. Clear?
Okay, sir.
Simply.
Okay.
Yes,
Sir.
sir. Yes, sir. It's clear.
Okay. So now we called capillary pressure. We formalized it. Okay, but in the laboratory also, what happens in the laboratory or in the field? There are some methods. So in the laboratory, first of all, we have to describe. We have to measure this capillary pressure. Okay. There are some ways of doing that. So let's a little bit examine the ways of these. Okay, how we will do that. The first one is the porous plate. Okay, so here you put your core plug. Okay, this is the actually a raw description of the material for porous plate measurement. Okay, there's a pressure regulator transducer here, digital voltmeters. There's an air compressor, and the cylinder takes the air. Okay, and then this air compressor push the air through to the line to the inside. It is actually a closed chamber, and your core plug is we put here, and it's capillary. It has a capillary contact with a powder. Okay, with a powder. There's a screen in here and the porous plate, and the differences between this diaphragm and the powder actually reflect to this part, and you make your reading in here in terms of capillary pressure. Okay, capillary pressure. Yeah, it has to be very sensitive. It has to be very sensitive. There is no other way. So the calibrations need to be done in oftenly. So this is porous disk method. We call it. So actually, the thing is how it. Let's talk a little bit about the procedure actually before passing to these plots. First of all, your core is saturated with water, okay, which contains it can be pure water or can be salty water brines by using the sodium chloride, calcium chloride, or potassium chloride. Okay, and to stabilize the clay minerals, actually these brines are needed. Okay, because which it tends to swell and dislodge when in contact with fresh water. So to prevent this, salty waters, we call it brines actually, can be used. Okay, so the saturated core, I saturated my core with the water 100%. Then it's placed on this porous disc. Okay, called this porous disc. Porous disc it put, and also this porous disc is saturated with 100% water. The powder in there saturated with the powder as well. Okay. This porous disc actually has finer pores than the rock sample has. Okay, what finer pores means? You actually, when we were discussing the porosity in last week, we described this one. Okay, how spherical it can be. In nature, we said that it's more heterogeneous, but we can make it homogeneous. So this is homogeneously made pores actually. Okay, so we know the blank empty parts between the pores. Exactly, we know it. Okay, it's shaped very fine, so has finer pores. Here, one of the rules is the permeability of the disc should be at least 10 times lower than the permeability of the core. Okay, if the ratio is less than 10, then there can be some problems in measurement. Okay, some errors in measurement. At least 10 times lower it has to be. Okay, so the pore size of the porous disc should be smaller enough to prevent penetration of the displacing fluid until the water saturation in the core has reached its irreducible value. Okay, the water saturation in the core has reached its irreducible value. Okay. So the pressure of the displacing fluid is increased in small increments. Step by step, small increments is increased, and each increase of pressure, the amount of water is displaced, and it monitored until it reaches static equilibrium. When it reaches static equilibrium, you say that, okay, the capillary pressure value, certain pressure value is this one. Okay. Actually, at the end of this, what happens when until it's reaching to this certain value, the capillary pressure is plotted as a function of water saturation, as shown in these two plots. Okay. So in the first plot, herein you see the in the first one, for example, you started to force. Okay, you started to force. And until it's reaching to certain irreducible saturation, water saturation level, it continues. And then when it reaches to irreducible water saturation, so we make the reverse. Okay, in the second path, we make the reverse until we are reaching to residual oil saturation. So I get two curves. Okay, so this is actually for a kind of core sample for a, which describes water wet. Actually, this is a water wet core sample. So when I make the same thing for an oil wet core sample, so I will get a figure like this. I will get a plot like this. So what are the main differences between these two? What do you see? Any comment? No?
So, teacher,
Yes.
again, just
Okay, so follow it. So I have two figures in here. One of them is oil wet, one of them is water wet. So what do you see? What is the differences between these two figures mainly? What you see the difference? What are the differences that you see in these two figures? Comment.
You mean 5.9 and 5.10?
5.9, 5.10. Yes. In 5.9, I am saying that this is a water wet system. In 5.10, I am saying that this is a oil wet system, and the capillary pressure curves of these two systems. So what you see? What are the differences of these two plots, these two figures? No? Okay, first of all, let's start with this one. I see the first difference that I see, it started from 1,0, right? 1,0. So it's 100% saturated with water, right? It can be saturated 100% with water because why? Because the rock lets it. Okay, your rock lets to saturate 100% with water because it's a water wet system. Here it started from somewhere here, right? So there is an oil because it's an oil wet rock already. Okay, oil wet rock means your rock likes oil. Your rock doesn't like water, so you cannot saturate 100% with water because your rock doesn't like water. Okay, so because of that, the starting point here is not 1, less than 1,0. Okay. Anyway, we started. It's going. Let's check this one. It reached a certain level of irreducible water saturation. And also this one reached to certain level of irreducible water saturation. This is okay, very good. So when I come to the second part, the curve that I will see, okay, when I am increasing the water saturation, I am displacing with water. The curve that I will see in here is shaper compared with the curve of the oil wet one. Okay, see the oil wet curve. This is shaper compared with the oil wet sample. Okay, and what happens? The area between these two will be higher. Okay, so when you compare this one, when you compare the behavior of two, okay, initially, you can say that this is oil wet or water wet. So when you see the area gap in here like this, so you will say that this is a kind of water wet rock, okay, water wet rock sample. When you see the area small like this and the shape is like this, okay, not the shape you see exponentially, it shows more slightly curve compared with this one, okay. So in this case, you will say that this is an oil wet rock, okay. You can say it directly. All right. So let's pass this to. Now another method is actually mercury injection. Okay. So in the mercury injection, we have a core plug in here. Okay. There's a pressure gauge, regulating valves, and cylinder again to take the air inside this one. Okay, inside the tube, inside the plug. And at this time you use mercury. Okay, you use a mercury. Actually, this mercury injection it has some disadvantages. First of all, for example, the mercury is injected into a core. It cannot be used for any other measurement as well later on, because mercury already injected and you cannot take the mercury inside from the core sample. So it cannot be safely removed. So it will be a disadvantage. Just once you can use your core sample. The second one, of course, all of you know, the mercury vapor is toxic, right? So, so it's strict safety precautions need to be taken. So not each laboratory is safely can do this one. Or in the field site, for example, if you have well site PVT tools, it will not be easy to use this tool. Actually, they mostly choose porous plate. It creates some tricky points. So because of that, they are not using this. They are not using this in most of times. Okay. So herein, again, how it works. Actually, it it makes a kind of mercury injection. Okay. First the mercury injection and then withdrawal of mercury it makes. Okay. It is actually a simple method. It can be conducted easily. You will inject the mercury and then take out. Where in the previous one, what we were doing the same thing for water, right? We were fulfilling with 100% with water, and we were monitoring the differences. So now here you have a core plug, and you are injecting directly. Okay, so the first one herein, the injection curve. Okay, so you start 1-0. Okay, so you start 1-0. So probably it means that if you start in 1-0, so your rack is mostly water wet, right? So you start from here, injection curve, mercury injection done, and then the withdrawal curve in here. You will see a shape like this. It's the behavior of mercury actually. Okay, behavior of mercury, because you are injecting water in here. Okay, injecting mercury in here, and you see a kind of shape like this. Okay, and then in the third one, reinjection curve. So you start again reinjection, and you see a curve like this. Okay, you see a curve like this. So the first thing in here actually, compared with the other method was using directly capillary pressures. This one you have to apply very high pressures. Okay, inside your plug you have to apply a very high pressure. So this is another disadvantage of this method actually. And the pressure is increased incrementally actually, slowly increased from 0 to maximum pressure that can be reached, but very high pressures needed. So this is another disadvantage. Okay, so the disadvantage of mercury injection, actually, you need to know this one. Okay. So another method we call centrifuge method. So this method actually, it's a very old method actually, the oldest method. It described in, as far as I remember, it's in 1951. Very old method, like Amot method. It was 1959. We will talk later on. So this is the old method. Here the core is placed in a cup containing an extended calibrated small diameter tube. Okay, a small diameter tube where the fluids displaced from the core by centrifugal force are collected. Okay, you collect the centrifugal force differences, and for example here the situation you see, my centrifuge shield is in the lower part. In the second, centrifuge shield is in the upper part. So actually the positions can change, and according to these positions, oil displacing, water displacing procedures get applied, and according to this, your centrifuge shield, you record your values, and then use your values like this. Okay, very old method, simple method compared with the others. A simple method. Centrifuge method, I can see that one. Let's talk about the procedure of this a little bit. I have written the procedure here. A weighted and measured core is saturated with brine under vacuum, and then reweighted to determine the weight of the brine saturating the core. So I record this weight, okay, as WB, okay, weight brine. The volume of brine in the saturated core, called VW, okay, volume of water, it says, actually brine, in the saturated core, is then determined by dividing the weight of the brine by its density, and the porosity is determined by dividing the volume of water in saturated core by the bulk volume of the core, we call VV. So VW, the brine in the saturated core, is equals to the brine, the weight of the brine saturating in the core divided by its density. Okay, so your porosity herein, the brine saturated, the volume of the brine saturated in the core divided by total bulk volume, okay. So the core is placed in the core holder, which is then filled with the oil to cover the core. First of all, we had done this with water, and in the second one we are doing this with oil. Okay, the core holder is placed in the centrifuge shield and then attached to the centrifuge arm in the reverse direction. Okay, so this time I will make the same thing with oil. All right, so later on, the rotational speed, which revolutions per minute actually, rotation speed, is increased in increments. At each incremental speed, the amount of the fluid is displaced is measured at successive intervals until fluid displacement stops. The capillary pressure associated with the displacement of water by oil, we call it curve 1, okay, water by oil, is calculated from the centrifugal force as described in the next step. Okay, here actually, when the rotor is filled with the core holders containing cores placed on opposite sides, the centrifuge cover is locked, and then the rotational speed is increased by increments again. Okay, so at each incremental speed, the amount of fluid displaced is measured as successful intervals until the fluid displacement stops. Okay, it works like this. So in the fourth step, the incremental rotational velocity and displacement oil are used to calculate the negative capillary pressure. So the positive one and the negative capillary pressure will be calculated as well as curve 3. You can see here. Okay. So in the part 2 and part 4, you cannot record this. Okay, you cannot record this because centrifuge is not enabled to make a recording on this one, because this is spontaneous emission. It's a kind of spontaneous emission part. You leave your core for a while, and when it reaches a certain value, you start the force again. Okay, you start the force again. So in the forcing part, displacement part, we can record this in this method. Okay. So in the fourth part, the core containing oil and water at an irreducible saturation is removed from the core holder and placed in another similar core holder and is filled with water until the core is completely submerged in the brine. Okay. So I have a two core samples. First one I used already. The second one, which is a neighbor core, maybe it has been taken from the same infrastructure. So I will use this same core for the second part of the procedure. Okay. So the cores once centrifuged at an incremental rotation velocities until oil can no longer be displaced from the core. And irreducible oil saturation I reached, I stop it. Okay. So this is the point of water saturation. This will be the point of water saturation corresponding to the residual oil saturation of the core actually. Okay. So what happens? The incremental rotational velocities and displaced oil are used to calculate the negative capillary pressure curve, which demonstrated here as curve 3. Okay, as curve 3. All right. So the core in the fifth step, the core which is now at a saturation equal to residual oil saturation actually. Is placed in another core holder until oil and the displacement from the initial saturation is conducted as described for the first displacement of water by oil. So at the end of this, I reach after spontaneous imbibition actually, I wait until it reaches adjustment balance, and then I make my forced displacement again. And I reach the curve 5 in here. Okay, I reach the curve 5 in here. So in this actually in this centrifuge capillary pressure method, capillary pressure measurement method, there are some formulations actually. Okay, so you remember 5.9 we already mentioned here, the equation 5.9. Which has been described actually with by Slobod et al. This formula. So the equation for capillary pressure in a centrifugal force field is derived by beginning this formula, 5.9. Okay, which was obtained for capillary rise in a straight tube. We already talked about this. And the centrifugal, in this case, the centrifugal acceleration, we call it A, is the volume, the square of the volume, the square of the rotational velocity divided by r. Okay, here the rotational velocity terms is centimeter per second. Okay, so and dividing this one and this rotational velocity formula, when we give it, it goes 2 times r, the radius, times n is here revolutions per minute. Okay, co-rotating, and this is revolution per minute. You can record this one when you are making your measurements, and you put it as n value and divide it by 60, gives you the rotational velocity. Okay, so here in 5.27 actually, dividing, when you divide your acceleration with the GC, okay, what you obtain the ratio of centrifugal acceleration to the gravitational acceleration. Okay, then you can substitute the A divided by GC for GC actually with the unit conversions. Okay, and you reach your A divided by GC and put it to your formula. You yield the capillary pressure at any height. Actually, according to the height, your pressures total pressure, your acceleration, and your gravitational force will be the functions of the description of your capillary pressure formula in this case. Okay, so herein, if you would like to take it in a certain distance, actually, you can demonstrate it. For example, in a core plug, you can put the differences of your core as RE and RI. RE and RI, and you can modify your formula according to, as you can see in 5.29 as well. Okay. So these are generic formulas which shows how the equipment make your capillary pressure measurement actually. Okay. So another thing here I can say. For an application for the core sample, so you can check the TIAP book, page 334. Okay, this will give you a good idea, and basic, of course, it's basic, but just it can give you a good idea regarding on how the capillary pressure data is calculated by using this centrifuge method. Okay. So now I will pass to the second part. Actually, in the second part we will talk about the wettability. Okay, the wettability. Actually, we already mentioned this one, right? When we are talking about capillary pressure, we already mentioned about this one, but we will talk a little bit more in details. So. Okay, let's start with the definition and term. Okay, so the wettability described actually as a tendency of a fluid to spread on a surface, on a solid surface, when this fluid and another immiscible fluid also in contact with that surface. So there are two fluids always and the solid surface always. Okay, so three different materials has to be in medium. Okay, in porous medium, or in normal conditions, in atmospheric conditions also you can do this, but three materials, one solid, two liquids, has to be involved in the situation. Okay, so two different terms. One of them is hydrophilic. We call, actually, hydrophilic is a general term which used in all materials. In material science also it's used. Hydrophilic means likes water. Okay, a surface likes water. So hydrophilic surface you say. Okay, if it likes water, you say hydrophilic surface. So in reservoir we say this water wet. Okay, if your rock sample surface likes water, we call it water wet. It's hydrophobic, doesn't like water. So in reservoir, it refers to oil wet. Okay. In normal, in material science, it's just hydrophobic. It can be compared with any other materials, not only oil. But here in reservoir, we call it oil wet direct. Okay. So what happens in a hydrophilic surface? Your water, when you spread it, your water has a tendency to directly spread on your surface. Okay, in a water wet situation. So if it is oil wet rock, what happens? Your rock will not like your water, right? Because it likes oil. So L2 is oil, L1 is water here. So your water will have a tendency to form droplets. Okay, to form droplets because your water also wants to escape from your surface, and your surface doesn't want it. So it wants to decrease the surface area, that penetration area, that's the surface area that it is contact with water. Okay, so how it can decrease it? By shaping it as droplets. Okay, so we call it hydrophobic surface. All right, so of course this one has it's very crucial, especially for the reservoirs doesn't have fractures. Okay, if your reservoir doesn't include fractures, which increases the permeability 10 to 100 times, for sandstone formations, for example, or some carbonates. This is very crucial because in that part, your matrix porosity and permeability will be the dominated mechanism. If your matrix permeability is the dominated mechanism to transmit your fluid from one pore to another, right? So your wettability will be the dominated, your capillary forces will be the dominated parameter. It affects the fluid flow directly. It affects the location of the location and the distribution of the fluid directly. It affects the oil trapping mechanisms as well. Okay, so the amount of the oil trapped is increased. So this is something that I never want, because it will be included to the irreducible oil saturation. So if you could not produce it, so you cannot use it. So you need to apply secondary methods, maybe tertiary methods to use it, to produce it. So it will create extra cost for me. So I don't want it. Okay. So this is very crucial. All right. So the range alteration of wettability. Actually, the wettability is affected by these factors. As you can see, 5 different factors in here. First of all, the rock mineralogy. The minerals in the pores as well as their distribution directly affect the wettability. Okay, so because of that, each reservoir and each rock sample is not same with another. Within the same reservoir also, if you are taking a core sample from well X1 and you take another core sample from well X2, it will be totally different, because the percentage of the composition, rock compositions, will be totally different. Okay, so when you are making the characterization of your reservoir, as much as data you can take will be very beneficial for you from each wells, from each locations of your reservoir. You have to take separate samples and analyze. This is very crucial. So equilibrium of the reservoir oil and formation water, okay, and continuous of the pore surface of the reservoir rock. This is also another parameter which affects the rock wettability. The absorption or deposition of oil constituents on the rock surface. That's actually also the reason of fractional wettability. Crude oil components are absorbed in certain areas of the rock. So a portion of the rock can be oil wet, while the rest is strongly water wet. So it directly, as I mentioned, can change. So because of that, it's crucial also, fractional wettability. The oil composition is another factor. Actually, if I am dealing with we described these oil types before. If I am dealing with a retrograde gas, it will have a different interaction with rock. If I am dealing with a heavy oil, it will have a different interaction with rock. Black oil different, dry gas totally different, right? So, for example, here when I'm talking about the black oil composition determines the solubility of the polar components. For example, a crude oil which has a poor solvent, for its own surfactants will have a greater propensity to change the wettability than the one compared with the one that has a good solvent. Okay, so the oil composition is crucial. And your reservoir conditions, but what I mean with your reservoir conditions, the temperature, pressure, and the saturation history of your reservoir, which affects your reservoir wettability. Previously, what happened to that reservoir? Is there any method applied? EOR method applied? Any other apart from oil and gas or water? Any other fluid involved to the game or not? Okay. So these are crucial. So another thing that I can say, of course, fractional wettability. By the way, don't mix the fractional wettability with mixed wettability. Fractional wettability, this is crucial. fractional wettability has a difference compared with the mixed wettability. Actually, fractional wettability means that scattered areas throughout the rock are strongly wet by oil, whereas the rest of the area is strongly water wet. Okay. Fractional wettability actually occurs when the surface of the rocks are composed of many minerals that have very different surface chemical properties, leading to the variations in wettability throughout the internal surface of the pores. Okay. But the mixed wettability is a special type of fractional wettability. Okay. Not covers all, some type of the fractional wettability. Unlike the fractional wettability, actually, the oil wet surfaces in mixed wettability assume specific locations, and form continuous paths through the larger pores, while the smaller pores remain water wet and contain no oil. Okay, my small pores still water wet. There is no oil in it because of the capillarity. Okay, it doesn't let oil come inside, but oil wet surfaces. There are some oil wet surfaces as well inside the reservoir rock. Okay, so it forms a continuous bed. Okay, yeah, my oil surface forms a continuous bed. Okay, compared with these tiny smaller pores which are water wet. Okay, so we call this mixed wettability. So these two don't mix these two. Actually, fractional and mixed are different terms. Okay. So wettability variation with depth. This is also another point. Rocks of hydrocarbon reservoirs are likely water wet before oil migration. Actually, all rocks in the beginning, all rocks were water wet. Okay. Think like this. All rocks were water wet in the beginning. Then, by the exposure to the oil and hydrocarbon content for many years, million years, so some rocks change to oil wet. Okay, mechanism is like this. So the reservoir actually, okay, it may change their wetting preference thereafter. It says the reservoir saturation history influences the reservoir wetting preference and the degree of these wetting preferences. So that's why we are using the contact angle. Okay, that's why we are using the contact angle. Actually, regardless of the rock mineralogy, rocks of hydrocarbon reservoirs are likely water wet. We said, right? So their behavior changed by the exposure of the oil, we said, for millions of years. Okay, so the reservoir saturation history influences the reservoir wetting preference and the degree of these wetting preferences. Certain. So in a thick oil-bearing formation, the wettability can vary with depth, with greater water wetting preferences near the bottom of the transition zone and the greater oil wetting preferences near its top. So oil-water contact, when you reach your oil-water contact, you will see mixed wettabilities. Well, when we said mixed wettabilities, you will see your mixed wettabilities in these zones, oil-water contact zones. Okay. So the higher zones have a greater capillary pressure, which can contract with the disjoining pressure and destabilize the water film, actually. Destabilize the water film and allowing surface active components in the oil to contact the solid. Okay? So lower in the structure, the solid surface mostly retain the water film. All right? So let's give an explanation of this. This is an equation which has been developed by Young, called Young equation. So herein, the facial tension between the solid surface and the liquid one. Okay, so my liquid one, liquid two, let's say water, oil. Okay, water, oil. So this will be here, by the way. the facial tension between the solid surface and L1. Okay, between the solid surface and L1, my facial tension here. Facial tension between the solid surface and L2, this one. Okay, it has to be here. Solid surface and L2, liquid 2. The interfacial tension between two immiscible fluids, and this is the one. Okay, the interfacial tension. And my theta is the contact angle. So, what affects my theta in this case? All these three. Okay, all these three. Think about that. The force here is stronger. SL1 is stronger. So what it will be? It will have a tendency to form droplets, right? Form droplets. So what it will be? My contact angle will increase up to oil width. Okay. So on the reverse, what if? Let's think that SL2 is higher compared with this one. So it will be has a tendency to spread on the surface directly. So the formula is the facial tension SL2 minus SL1. Facial tension SL1 is equal to the interfacial tension times my contact angle. Okay? Interfacial tension of these two liquids times my contact angle. So this is the basic equation. So let's shape it a little bit. How we will shape it? For a liquid solid system, we said that this is the formula. I showed it already, right? For an air liquid solid system, so in this time I put a term called SV. Okay, solid air facial tension. Solid air facial tension. So L1V and L2V is liquid air facial tensions. Liquid air facial tensions. And I already mentioned the liquid solid system. So when I take my cos theta from this part as a function of cos theta 1 and cos theta 2. In other words, what I am doing, I am trying to describe a liquid solid system by using air liquid solid system results. I have two air liquid solid system result, and I want to make a calculation for liquid solid system. So the formula will be like this. Okay, like this. So facial tension L1 cos theta 1, facial tension L2 cos theta 2 divided by the interfacial tension of L2 L1. All right. So this is the Young equation. Okay. So rock wettability. Here you see three different scenarios, three different paths. First of all, the first one, I described this already, okay? And the B shows water and oil interface and your contact angle, okay? And we already described all of this, right? So your water, what happens? Your oil start to stay in the solid surface, and here what happens? Your water want to stay in the solid surface. So because of that, this is water wet, this is oil wet, right? So okay, herein there are some values for contact angle. What are these values? Actually, if I want to describe a rock as water wet, so it has to get values between 0 to 75. Actually, in some literature values between 60 to 75. Some of them shows up to 60 water wet. Some of them shows up to 75. But because I put it here as 60 to 75 according to the literature values. So my minimum maximum values is this one for water wet. So for neutral wet, some of them, as I told, 60 to 75, they start as neutral wet, and 105 to 130, okay, they call it neutral wet. Up to 132, I saw. Morrow, actually, it was Morrow's study. 132 maximum, it called neutral wet, okay. So for the oil wet, some work starts from 105, but mainly in the last years they called 130 around. to 180 degrees, we call it oil wet. Okay. So when you are making your calculations, your descriptions of your contact angle, when you made them, so you have to assume, you have to actually consider these wetting values in the literature. So here another view of this. For example, it says for Morrow, actually I used Morrow because this is the most acceptable one in the literature, the accepted one. So it used 0 to 62 as water wet, 62 to 133 intermediate wet region, 80 to 100 it's neutral wet, it calls neutral wet. Okay, so 133 to 180 it calls oil wet actually. Okay, so Triber et al. Described this one between 75 and 105. Schillinger and Yen described this one 80 to 100. Okay, this intermediate zone. All right. So there are some wettability measurement methods in the literature. There are some wettability measurement methods. These are AMOT, the most common ones, AMOT wettability methods, USPM wettability method, combined AMOT-Harvey USPM method, and contact angle methods. Okay. All of them has advantage, all of them has disadvantage. In last years also, in 2014, we developed another method with my supervisor in Abu Dhabi. We succeed to develop another method called Rising Core, RIC. It also succeed, and we got the patent of this one. We succeed to get the patent, US patent of this one. It's now applying in Total and ADNOC of Abu Dhabi. So it's one of the acceptable methods in future times. It will be, and it will be an alternative method compared with these ones actually. But now I did not mention that one. Now just let's go with the generic ones. Of course, all these have limitations. Okay, so some of them has imprecise wettability bands. Some of them are very demanding to experimental setup. So operational input is very crucial. Some of them are very demanding to experimental procedures. So operational input also human dependent. I mean, okay. So, for example, USPM test cannot determine whether a system has fractional or mixed wettability. So, I gave you the difference of two. It doesn't determine it's fractional or mixed. Okay. So these type of limitations are available for all these methods. So let me start with the AMOT. Quickly, I will pass this part. For the AMOT wettability index, the procedure involves 5 different stages actually. Okay. The first of all, I started my test at the residual oil saturation. Okay. Residual oil saturation. So therefore, the fluids are reduced to SOR. I mean SOR value. So I start to my displacement, forced displacement of oil, and my displacement started where up to irreducible water saturation, right? Irreducible water saturation. So what happens? Sorry. So what happens? The core is immersed in oil for 20 hours, and the amount of water displaced by spontaneous immersion of oil, if any, is recorded as VWSP. So I am in SOR value somewhere here, and I leave it for 20 hours. So what happens? This white curve happens. So this white curve is a spontaneous immersion part. Okay, naturally you are leaving it according to the atmospheric conditions or vacuum conditions. Mostly I'm using vacuum conditions, -1 atmosphere, and then you leave it in your spontaneous immersion here, and you record your value of WSP, VWSP. Okay, and then the water is displaced to the residual water saturation. Okay, residual water saturation with oil. You make a first displacement with oil, and until you reach to residual water saturation. So when you reach to residual water saturation, actually irreducible water saturation, so you record your VWT. Okay, another term called VWT. So you record this as well. Okay, how many? So this gives you the volume, actually, volume displaced. Okay, and later on, the core is immersed in brine for 20 hours. Again, spontaneous immersion again. Okay, so this time what happens? I put it inside the brine for 20 hours, mostly in vacuum. Okay, so leave it and see how much of the oil will be changed. Okay, it will be changed with water phase. Oil will go out, water come inside the oil. So this calls spontaneous immersion, and I reach to a certain value. Okay, and after 20 hours, I regard the volume changed as VOSP. Okay, and then I start the displacement again with water this time. And then when I make my force displacement with water, I reach to a certain level and I record this as VOT. All right, VOT. So after recording all these parameters, all these volumes, okay, so what happens? I described a wettability index value, IW, we call, and VOSP divided by VOT minus VWSP divided by VWT. Okay, this gives me the wettability index. Okay, this is the difference between the water and oil phases. Okay, so it's written here as well. Preferentially, water-wet cores are characterized by a positive displacement by water ratio, and the value of 0 for displacement by oil ratio. Cores that are oil-wet shows a positive value for the displacement by oil ratio and 0 for the displacement by water ratio. Okay, so it gives you an idea, to sum up, it gives you an idea regarding on, according to the results from 0 to 1. All right, so it gives you an idea regarding on your wettability value of your core sample directly by seeing the IW results. Okay, so very similar method according to this compared with this one, very similar method, but have some little differences. We call USBM, United States Bureau of Mines. United States Bureau of Mines has developed this one. So here we described IU at this time. Okay, IU, and this is the log of the areas. What are these areas? What are these areas? Same procedure we are applying. Okay, first of all, the first difference here, 100% you saturate your log. Okay, 100% saturate your log. And then after that, after the saturation, you make a force displacement. Okay, you make your force displacement. And then after your force displacement, you apply the reverse procedure of Amott method. Okay, in Amott method, what you were doing, you were starting directly from this one. SW, okay, as your procedure was starting from this point. Here, your procedure is starting from this point, okay, in irreducible water saturation. So you apply the same procedure. So after that, what you do, you calculate the areas, two different areas of these curves. So A1 and A2, A1 and A2, A1 and A2. Okay, so you calculate these areas and get the ratio of these areas and the log of that. So this gives you the value of IU. Okay, herein the increasing positive values to infinity plus infinity indicates increasing preferential water wetting to infinite water wettability. Because why? Because when you increase your area, okay, let's think that it's going to certain plus infinity at this time. So what will your A1 will increase, right? Your A1 will increase. So it will increase the preferential water wettability property, water wetting property. A value of 0 represents the equal wetting of rock by fluids. It's natural wettability called. The increasing negative values to minus infinity indicates increasing preferential oil wetting to infinite oil wettability. So when it's going to minus oil wet, when it's going to plus, we call it water wet. It will be okay. All right. So there is another method called Amott USPM combined wettability test. So in this case, you start again. You start by 100% saturation of water, and displace. You make your force displacement, and then you again you record your values. And at this time, you will use the values that you recorded like Amott method, but you will use what happens. I am using the parameters like Amott method, the volume change, but I started from 100% water saturation, like USPM. So this is a kind of combination of Amott and USPM. Okay. So these here, the parameters: amount of water produced by oil injection, amount of oil produced by water injection, water produced by spontaneous oil imbibition, and what oil produced by spontaneous water imbibition, like Amott. All the way is same like Amott. So these are the formulas of the description of IW and IO, and the difference of IW and IO give me the parameter of Amott-Harvey, Amott-Harvey, okay, AH, we say. Okay, combination of these two. In last years, actually, this one is preferred, Amott-Harvey. So it's most preferred method actually. So another method is contact angle measurements. These are very basic, and the idea of this one is the observation. Mostly you use a camera or something which focus to the droplet. You use a droplet and you observe the droplet, and your camera has a certain properties which measures the contact angle value. And when you are observing, okay, you need, of course, for this one you need a solid surface. Your rock surface need to be polished. You cannot use a porous surface, of course. You need to polish your rock surface to observe your droplet, of course. So there are some different methods, some different procedures applied to some. For example, A, B, and C here illustrates the procedure where the solid plate is suspended horizontally, okay, below the surface of a clear, that I said polished, right? Clear, actually, rock surface. Oil and a drop of water is placed on this solid, okay. So in another one, you suspend the plate horizontally in the water and place a drop of oil on the bottom of the plate this time, okay? And you make your observation and you record your data, okay? Here, of course, same analysis applied, and the contact angle is measured through the water phase section, okay? So these two methods both can be applied in sessile drop methods, okay? This is sessile drop method. One another method called modified sessile drop method, okay? So in this modified one, this time you have two different surfaces which has crystal polished surface, you can say. So here what happens, it moves one of these surfaces, and it records the water advancing contact angle, okay? So by using this one also you can have an idea regarding on your contact angle, okay? Very basic. I put it as a basic step, so no worries. So what about the wettability, effect of wettability on oil recovery? Actually, it's another thing. So for example, here again, this has been taken from Tiap's book. So for recovery efficiency compared with the water injected, okay, so 5 different core samples can be seen here. The silicone is used actually to make a displacement, okay, and according to this, the wettability values has given here, okay. So the wettability values, you see 0.6, 0.1, minus 0.2, and the rest are minus, okay. So For the first one, it has the highest recovery efficiency. According to this one, when it is in positive, you said that this is a water wet drug. So drug doesn't like oil. If it doesn't like oil, so it lets you to produce your oil. So your recovery efficiency will be higher compared with the other three. Okay, the other three. So in terms of relative permeability curves, you can say that the first one is water wet, and the second one is oil wet. Who can tell me about these two plots? How I understand? There's a very easy description. How I understand this A is water wet and the B is B is oil wet. Any idea? Are you with me?
Yes.
Yes,
Yes.
teacher.
We have an idea.
Very good. So
Yes.
now I said that A is water wet and B is oil wet. How I can understand? There's a very easy way of description for this. How I understand? There are two. You see, there are two curves.
Is oil wet.
Tell me.
Which one is oil wet, you said?
Which one?
Which one is oil wet, you said, teacher?
It's right at below.
Okay, see, this A, this plot, shows a water wet behavior. Okay, and this plot shows an oil wet behavior. How I understand this? How I understand that the first plot is water wet.
From the line which is started after 0.2.
For a line which start at, okay, one part of, yeah, this one. You said this is starting after 0.2, this started before 0.2.
Yes.
Relative permeability is greater in water wet.
Relative permeability?
Is greater.
Tell me again.
Wet.
Relative permeability is greater compared with these two.
Yes.
Acceptable, but there is another thing tells about the wettability. Very basic. Okay, this is what is this? What is this?
Is there
What
any
is
relation
it?
about the imbibition or dye range?
Again, I could not get your voice.
Is there any relation of this path with dye range or imbibition?
This is relative permeability curve. Okay, this is relative permeability curve. So it gives you your relative permeability behavior with the changing water saturation. Of course, there's a displacement in here. Okay, so this is water saturation. So your water saturation is changing inside your core. Okay, so when your water saturation is changed, okay, let me say that. So this starts from here and comes up to here, maximum, right? So your water saturation is around 0.7. Okay, so for oil displacement, it shows a kind of curve like this. The cross point of these two curves, where is it? 0.68 maybe, right? 0.68 something, right? Here, the cross point is 0.4445 maybe, right? So if my cross point is a very easy description, is above 0.5, okay, if my cross point is above 0.5, then you will say it's water wet. Okay, so in most cases it's like that. If my cross point of two curves is below 0.5, 0.45 here, for example, you will say it's oil wet. Okay. In most cases, if your rack is includes too much wax in it, for example, not fracture, it's wax. Okay, so it's very homogeneous. Then it can have some problems. But for a sandstone, for example, for a carbonate, which is representative as homogeneous. Okay, so it will definitely show that the cross point definitely show that this is if it is higher than 0.5 water weight, lower than 0.5 oil weight. Okay, clear? I think clear, right?
Yes,
Yes,
teacher.
yes.
It's
Okay,
clear.
this can be one of your questions in futures. Okay, so let's go. Okay, so we will mention this wettability term in logs as well, in resistivity logs as well. But now, first of all, in lab scale, in this week, we will discuss this in lab scale. So there's an effect of this electrical, the wettability in electrical resistivity. So when the rock is partially saturated with a hydrocarbon, oil, gas, whatever, the resistivity of rock is increased due to non-conductive properties of hydrocarbons. Okay, non-conductive properties of hydrocarbons. Hydrocarbons are not like water, not too much conductive. Water is a very conductive material, right? So your hydrocarbon is not like that. So this is a very good thing because you understand you reach to a hydrocarbon or not. What we said in logs, what we were doing, we were reflecting, we were sending a signal and getting the reflection, electrical signal, sending, getting the reflection. So the conductiveness of hydrocarbons are not like water. So this is a very good advantage because I can understand the parts that include hydrocarbons, right? So this is very important. So wettability is an important factor for brine distribution, which contributes to the change of resistivity in this case. So for water wet, brine is continuous, so the decrease of the cross-sectional area head can conduct flow will lead to the increase of resistivity. Oil wet, brine is discontinuous. Brine is discontinuous, so the electrical resistivity will increase at a faster rate than in water wet. Okay, so conductiveness of water is very high. If I am talking about water wet, there always be the brine will be included all the parts of your reservoir in capillary level because what we said, your rock likes brine, so it has a tendency to spread. So your irreducible water saturation will be higher, and it will be every part of your reservoir, the water. But in oil wet, it's not like this because some part of rocks will include oil in its surface. So there will be some discontinuities. Okay, so because of that, in terms of electrical signals, you can definitely understand it's water wet or oil wet. It includes soil or not. Okay, so let me show you a very basic, very old lab equipment. This is an NMR actually, nuclear magnetic resonance. It describes it senses the electrical signals and gets the resistivity. Okay, in lab scale. So it's known as NMR resonance of fluids in the vicinity of solids. That can be quite different from that in bulk fluids. We already explained this one, right? So these effects are useful to characterization of porous fluids and fluid distribution with NMR measurements. This is in lab scale. So in our next topics, we will see the version of this in well scale, in field scale. Okay, so as logs. All right. So what we said, I will talk a little bit about the aging procedure. What we said actually, we said that all the rocks were water wet in the beginning. Okay. So now you want to make an experiment in your laboratory and you have water wet samples. For example, there are some rocks called Berea, for example. They are selling these rocks from US. If you want to make your lab measurement, you have to buy this one. But you want to make your sample as oil wet, okay? As oil wet. So how you will apply this one? There's a procedure actually to make your water wet rock as oil wet, okay? We call it aging procedure, okay? there is a technique of this one. For example, your first of all, you saturate your core plug with brine 100%. You mount the core in a cell, okay, and you flood it with oil, okay, at least 10 pore volume, 10 times pore volume. You calculate your pore volume inside your core sample. At least 10 times of your pore volume, you float oil, okay, and this place the rock. And then age the core in a crude oil at an elevated temperature. For example, it says here 45 degrees. When I was making this, I was using much more, up to 70 degrees, okay, in soak sleds. You know, there are soak sleds which heat, gives a heat in from the lower part, and you age your cores for 7-8 weeks, okay. So, and of course, as a procedure, you flip and shake the core in every 10 days. And after 7 weeks, 8 weeks, you make your core oil wet. You directly see this. And I made, when I was making my contact angle measurements, I remember it was a water wet previously. And I got 178 degree contact angle from a core sample which made oil wet, okay? Previously it was water wet and we make it oil wet. So, effect of wettability in electrical resistivity, we said. Here in the figure, you see two different plots, right? Normalized T2 is said, normalized as cumulative volume. So herein actually, if you see a longer T2, longer peak value like this, longer peak value, your surface relaxivity is smaller than water. Okay. So if you see initial water saturation is wider than compared with this peak, so you say oil wet. Okay. So you see different two different behaviors. If you see a peak like this, you say water wet. If you see a tendency like this, you see oil. Okay? So the resistivity index, also resistivity index called IR, is the ratio of RT to RO. What is RT? RT is the true resistivity of formation contains hydrocarbon. Okay. And RO is the resistivity of formation when 100% saturated with water. Okay, this is the actual one. This is the 100% saturated with water. So the ratio of this gives you the resistivity index. So according to the brine saturation differences, your resistivity index will show a behavior like this, line and decreasing. When your brine saturation is increasing, your resistivity index decreasing as a certain line. Okay, so herein I can say you that you check the problems in TIAP's book at the end of the chapter 6. These will be crucial. If you have any questions, I can answer that inside the week. You can ask me, no worries. So this will be the topics that I will mention, that I already mentioned in week 2. So next week we will start with course with logs. Okay, we will start with logs actually. We will start with logs. So let me take a picture. So now we are 27 people. I see here. So I will take this one as who is absent, who is here. I want to know. Okay. All right, guys. So end of week 2. If you have any questions, I will be glad to answer your questions related to this one. As I told you, next week we will pass to. We are starting to the logs. Okay. So any questions?
Yeah, teacher, I have a question.
Please.
Teacher, you said the 3 models in the section capillarysis. And firstly, the oil wetting, third part is water wetting, and second part. And there is, you said the degree is 90 degree. I didn't understand. I think it must be the 180 degree. Can you please
Let's go.
teach this part?
Somewhere here. This one?
No, teacher. You said the three figures. Capillary tubes.
Capillary tubes before.
Yes, they in the previous slides.
This one. Wait. Okay, I got that. This one, huh?
Yes. The
Okay.
second part, you said the 90 degree. I didn't understand this.
Okay, the second part here. All right. So, how I can explain this one? The pressure differences between oil and water phase here are almost zero. Okay. So when they both in contact with the solid surface, right? They both in contact with solid surface, but they don't have a difference compared with the solid surface is not selecting one of the fluid. Okay, the solid surface is behaving same to oil and water. So because of that you will not see any difference like this, any concave, any convex behavior, or any pressure differences like this. You don't see anything. So it means that the preference of your solid surface, capillary tube surface, is same to oil and water. Okay. So in reservoir you see the same thing as well. To oil and water, your rock can behave same. Okay. In some parts it can take water phase, in some parts oil phase. Okay. So when you check your sample, core sample, for example, you make a CT scan, you see that there is no differences of the rock behavior to any oil phase or water phase. Okay. So in that case, experimentally, when you make this one, you satisfy these conditions and you make this one, what happens? The theta of this, there is no concave or convex, right? There is no convex as well. There is no concave as well. So there is no theta angle in here. So when there is no theta angle, so your line, this line, will be here. Okay. So the angle will be 90 degree. 90 degree, right? So
Between tube and fluid surface.
Yes. Because why? Because your solid surface doesn't select any of these. So because of that, your line, as you can see here, two lines, your line will be same with your oil-water contact. Okay, when it is same with your oil-water contact, there is no concave or convex behavior. So your angle is already 90 degree. Okay, so if it is 90 degree, so what happens? It's neutral wet. It's not selecting any of them, right? So when, okay, let's talk like this. When it becomes 180 degree, see, I am saying you, this is 140 degree, for example, okay? 140 degree. So when it becomes directly same with the capillary tube, which is, by the way, which is not possible, okay? Which is not possible. You can reach up to 170 whatever, but it's not possible in practice. Theoretically, yes, but in practice, it's not possible. So when it's become in the same direction with your capillary tube, then you say 180 degree. Then you say 180 degree. Okay, but it's not like that. This is 90 degree angle it's making. Okay, so you can understand from the behavior, actually. If you don't want to talk about the contact angles, you can understand it from the behavior, actually. Okay, here in neutral way, it's neutral. See, there's no preference. It's neutral already, so it has to be 90 degree, you can say. Okay.
Yeah, teacher, understandable. Thank you.
Okay. Other question? Place that you don't understand. I'm pressing the slash slowly. No?
No question.
Okay, so let's finish this week. So see you in next Saturday.
Okay, thank you, sir. Have a
Have a
good day.
good week.
Thank you very much.
Thank you.
So some
Bye.
of you recorded that one, right?
Yes, yes,
Oh.
it will upload
Yes,
by
Yes,
itself.
we
Okay, please stop the recording, and let's see if we can see that or not. Okay.